Okay, so yeah, our group for our senior project will be producing a high-resolution headband document scanner and transmitter using digital imaging algorithms. This is our general outline. This is pretty much what we'll be talking about for this presentation. My name is Andy Cianville. I'm the project manager. I am a computer engineer, and I'm also the software manager for this project.
Hi, my name is Adia Khalik, and I'm a computer engineer.
Hi, my name is Gustavo Zarate, and I'm also a computer engineer.
Hi, my name is Jorge Vasquez, and I'm an electrical engineer, also hardware manager.
Good morning, everybody. Saad Hussain, also electrical engineer.
For project motivation, we used Smalley Farms, a facility located in Staten Island. It has a work facility for disabled people. Some of the job is watering plants and shredding bulk paper in bulk. Randy was our main focus at Smalley Farms, and his immobile from the neck down with some control of the fingers. Randy requested to work in the office with the ability to scan objects with his own limitations. The idea was creating a wireless scanner that transferred documents to the computer without physical involvement. As the big picture, that's Randy. Um, was just giving Randy and other individuals with similar characteristics the possibility to work at the facility and in different environments. The idea came from an actual site visit when we met Randy in his daily situations. The idea of scanning seems simple, but it contributes to the work facility and also motivates them adapting to their surroundings.
So for our project selection, we came up with a few alternatives. The first one being a rover, which would assist the user. However, the rover would potentially be an inconvenience in terms of maintenance and it being too bulky to have around. Another alternative was creating glasses instead of a headband. Although this seems to be a good approach for portability, this would create some issues concerning the ease of use for the user and in terms of the microcontroller and battery having to be compact enough to not cause a disturbance for usability. So in terms of the process, we plan on implementing a portable camera attached to a headband for capturing information and utilizing OCR algorithms for identification of the data. Our project intends to have a positive societal impact by taking into consideration the needs of individuals who are disabled and attempting to make a difference through a system which would allow them to have a role in the workforce. This intention would hopefully provide a sense of opportunity in the Small Farm Staten Island location and the surrounding community. So catering to even a few individuals may have the potential to make an impact for others with similar conditions.
Hello, once again, everybody. So after meeting with the creative program people and Randy himself, my team and I were able to come up with some marketing requirements. The first one is that the system must be lightweight and portable. Main reason for that is it's going to be mounted on the person himself, so not to cause him any discomfort. System must be able to take high resolution pictures, very important for the scanning aspect of our system. If it's a good picture, the result is going to be more accurate. The system has to be robust for daily use. Uh, People are we're expecting people to use this 3, 4 to 5 days a week, which is a normal work week. So definitely robustness for daily use is important. It has to be easy to use. Making this for disabled people, uh, have to make it as convenient for them as possible. And the system has to be able to seamlessly transfer data. This is so that no other third person has to have any interaction with the system to transfer the data pretty much. Next slide. Our engineering requirements as a result for our marketing requirements are the camera. We chose to be 5 megapixels and have autofocus capabilities. Uh, This is pretty self-explanatory. 5 megapixels is good enough for a high-resolution picture, and that would again give us a accurate result for a scan. The second one is the electronics and camera must be protected by shatterproof material to prevent damage. This is for the longevity of the product itself. It should have a reasonable battery life. We're aiming for 5 hours. This is something that might change due to limitations of the available batteries to us. Customer should have interaction with one button. This is again people we're making this for are physically disabled people. So if we can give them interaction and control over the system with one button, that would be ideal and very helpful for them. The next one is the customer will have an 8-inch tablet with a dedicated application. And the purpose of the application is that so that they have a real-time visual of whatever the camera is seeing for them to be able to take a good, accurate picture, at least have the whole document in the frame. The scanner should have an adjustable headband and should not exceed more than 150 grams. Again, it's going to be mounted on, put on a person. So the weight aspect of it is very important. It should be able to, the system should be able to transfer data through Bluetooth. Main reason we came up with the wireless transfer of data was we did not want a lot of wires around the user himself. And then later we got locked onto the Bluetooth technology because we won't be able to do it over Wi-Fi due to problems on our client side. The software should be upgradable. So this basically comes in where we are trying to make a system like Jorge previously said, for more people in relatively the same situation. So it should be relatively upgradable. Like if somebody does not have, let's say, mobility in their neck somehow, we should be able to somehow manipulate the system to fit their needs. The last one is object recognition algorithm should have 90% accuracy at least. And again, this would be very important to have a good final scanned copy, which is going to be accurate enough.
So for our objectives tree, we've determined 3 selection criteria as before mentioned, such as high quality imagery, being user friendly, and portability, to allow for to have like a high resolution format, being lightweight and comfortable, and so that it's not burdensome to wear and operate. So as you can see, these criteria are ranked based on importance, and these 3 criteria are further divided into sub-characteristics and ranked accordingly, once again, based on the needs and market requirements. We can't hear you.
Sorry, muted.
Sorry about that. So this is overall description of our system on how data is generally going to flow. And starting from the left side of the image, it's the image sensor captures visual data and sends this over to the image processor. And the raw data right there in between is actually the format of the data itself. So the image goes to the image processor. I mean, the raw data goes to the image processor, gets processed into an image file, and then that gets sent over to the scanning software for it to have a scan document. And then another copy of it goes to the LCD screen to be displayed to the user, pretty much.
So for the theory aspect of the system, finding the 4 corner points of the document using edge detection can be done as shown in the before picture. But we must reorder the points in order to prepare them for the warping. The equation shown below calculates the order of the points by the x and y coordinate of each point, where they are added and compared to the smallest sum of x and y, where it is assigned to 0.0, and the largest point is assigned to 0.3. The same process was done for the other 2 points from least to greatest with these methods. The points were rearranged in order shown in the after picture so that it would be used in the warping. Here is the UML diagram of the OCR, and here we can see that there are 4 actors, which are the camera, the display, the microcontroller, and the document database. The camera will scan the document and send the data to the microcontroller where it will process the image. However, before this, the display will show a real-time view of to the user, so they are able to see what they're trying to capture. Once the microcontroller receives the image file, it will process the image file and be converted to a PDF, and then send that PDF file through Bluetooth to the computer database where all the scanned documents will be stored. Below, we present the functional decomposition level 0 diagram and tables that describe the input and output of the headband document scanner. The headband document scanner will be provided with 5 volts of power and will take an input of an image data in JPEG or PNG, which will output a compiled PDF file from the software system. Here's a more detailed and closer look into the functional decomposition. The camera captures an image of the document and uses image detection algorithm to only capture a piece of paper and not other random objects that is in its view. The microcontroller completes 2 tasks, which provides a live feed of the camera to help the user be able to see what they are capturing. And the second task of the microcontroller is processing the image data. Once the software engine receives the image file, it will then process the file in the optical character recognition algorithm and convert the warped image file to a scanned PDF document, which will be sent from the software engine via Bluetooth to the computer document database.
Yes, so for the hardware design, we actually divided our work into 2 separate categories. The first one is power design, and under this, we pretty much made a regulated power supply. And the second point, which is actually a recent addition to our requirements in some ways, if that's one way to put it, is fast charging due to the lower battery life that we are giving them now, which is 5 hours, as I stated before. The regulated power supply is actually on the next slide, but going to the fast charging, we are implementing it using a Texas Instrument IC, model number B25792. It's basically a buck boost charger, and this chip is going to actually be deployed on the battery side, so inside the headband scanner itself. The charger side, which would be the wall piece, which supplies the power to charge, would also have another chip, but we, like I said, it's a very recent development, not a maybe 3 days ago. So we were not able to come up with a chip for that for now, but that would definitely be something that is going to be used on the charger side. The next thing is the camera design. For now, we only have the LED flash drive circuitry for this. Again, this is going to be deployed using IC from Texas Instruments, model number TPS51325, and it is basically able to run up to 2 LEDs at the same time, which we are planning on deploying 2 LEDs for our camera. Next slide. This is pretty much a piece-by schematic of our power supply. It's pretty self-explanatory in some ways. I'll just go over it real quick. Takes in 115 volts, which is regular AC to our houses. Transformer step down, diode rectifier bridge, smoothing capacitor, and in the end, R2 is a simulated load, which is I just went with 1K because I was trying to just get a graph. And then the right side pretty much shows our DC output. And then this DC output is the thing I'm missing on this schematic would be a voltage regulator, which would go in between C1 and R2. Reason for that is I had issues with libraries and I was not able to simulate the circuit with the voltage regulator. It was not making any differences. But yes, basically that is the output for our power supplies so far.
Okay, so for our software design, we implemented a code that involves a process of reading an image, warping an image, and converting that image into a PDF. As shown as on the flowchart, it shows our general process. First, it reads an image and then prepares the image by processes of graying, blurring, dilation, and then it attempts to find the contours and 4 points of the image, which is like the 4 edge points. And if the 4 points are found, it will go on and warp the image. But if it isn't, it will fail and you have to read another image. After the warping, it will sharpen the image to make it more clearer, and it will check to see if there's any text or if the text is legible. If there's any text or legible, it'll convert to PDF. However, if it isn't, it'll fail and you have to read another image. You have a video showing the process, but however, it's kind of long, so I'll go through the different steps of it. This is generally the code of what we use. There was three points, the one that warps the image, one that sharpens the image, and one that converts it to PDF. If I go through it in different parts, the gray, it first grays the image. That's not it. First grays the image, and next it blurs the image. Yes, it blurs the image. It blurs it out, smoothens it, makes sure that it lessens the visual noise. Next up is the dilation. As you can see, it outlines the borders of the page, which helps for the contouring. The next part is the contouring and the 4 edge points. As you can see, it successfully contoured the page. And with the 4 points, the red numbers are the ones or the original points, and the yellow numbers are the reordered points in order for it to get a successful warp. The warp is the next step is the warping, which it converts that image and manipulates it into a top-down close-up image. And the next part is the last part is the PDF. It converts it into a searchable PDF, and it's able to be highlighted, and you can copy and paste it anywhere you want. So for the next part is the test and results analysis. One of the tests that we took was an accuracy test of the PDF conversion. We did that by comparing the original and the PDF conversion and putting on the Word doc, and accuracy was based on sentence word similarity. The results for a test was that it was 92% accurate compared to our engineering requirement that the object recognition algorithm would need to be at least 90% accurate, so it was a success. This is our corrective actions and iterations charts. This is the iterations that we made till now concerning software code. It contains multiple unit integration acceptance tests like the OpenCV test, which is the image warping, image magic, which is the sharpening, and the tesseract, which is the PDF conversion, as well as other combinations of those codes in the overall accuracy test. One of the iterations that we made was the resizing. Before we were using resizing, which shrunk the image so we can see it better. However, when we actually ran the code for the warping, as you can see in the full 4, it came out really blurry. You couldn't read the words. And once we realized it was the resizing that was causing that problem, we pretty much put it to a 1-to-1 scale, which pretty much is the full image. It won't do any resizing. So as seen by the after result, you can actually read the words, and when it goes to the actual PDF conversion, it'll actually be able to do something with that text. This is our project schedule that we made in the beginning of the year. It might be kind of small, but because we added more as we went on with the project. For what we said we're going to do this semester, there's software research, OCR implementation, and for the hardware, there's the research, microcontroller implementation, and the camera implementation. And for our 40% milestone, we said we'd get the implementation done for the OCR, which is the optical character recognition for text. We got that done, plus more, since we also got the image detection software done. In terms for the hardware, we said that we would obtain the microcontroller and the camera, but due to us not having the budget, because the PA program haven't gave it to us yet, we've kind of been incomplete with that. And this is the overall cost analysis bill of materials. This is like everything that we're going to need throughout this whole project. There's the camera that we need to take videos and images, the battery in order to keep the whole thing operational. There's the microcontroller, which is the whole like the workings of this scanner. The 3D printer, the 3D printed enclosure, which will protect the whole entire scanner. Circuit designs, PCBs for like, we need multiple of them for different parts, such as the power supply, the flash unit, and the flash unit, as I said, will help in like low lit environments, so you can take a better picture. There's the user interface, so you can actually interact with the actual software. The tablet, in order so that a person can have a real-time video of what the camera sees using the app that we'll also make. and various electronic components that will be used to construct these different other parts.
For the conclusion, we encountered several challenges regarding the microcontroller, the camera, and the libraries. But overall, we made good progress despite the budget complications. For future works, we're working on the app to connect the live video and the microcontroller. We're planning on improving the contouring implementation, and also building a physical power supply with a charging circuit, as well as the flash unit. Finally, just we plan on actually beginning the testing the whole unit itself, from the software and the hardware. As code standards and constraints, imaging profile, sending image and converting it to receiving devices, file transfer profile, which adds, manipulates and transfer objects to another system, video distribution profile, the distribution of video streaming and video content, UL 1642, which is standard safety for lithium and lithium-ion batteries, and BC 1.2, which is USB charging protocol and specifications.
So for the ethics of our project, by acknowledging the end user disabilities and keeping in mind that our project may impact others on a larger scale, the scanner's reliability, safety, and ease of use are at the forefront of our design and process. We've also acknowledged the IEEE and NSP Code of Ethics and will abide by rules at all times. We value and understand the importance of upholding the highest standards of integrity, responsibility, and ethical conduct. And our part does not infringe on any patents or copyright, and we haven't reverse engineered another product to base our design off of. So the software development side of the project involved a multidisciplinary approach involving computer science and engineering, computer vision, and various image processing techniques. We used a computer vision library known as OpenCV for real-time processing of images and utilizing certain library functions to initiate the processing of the images, such as using Gaussian blur, canny, edge detection, dilation, contouring, and the warping mechanism. So the combination of the mentioned disciplines so far have taught us new concepts related to digital image processing, object recognition, and OCR algorithm, as well as computer science topics pertaining to software modeling and design.
For the hardware complex engineering, we used P-Splice software to build a schematic of the power and charging circuit. Our current schematic displays a step-down transformer that goes from a 115 volt AC source to a 9.2 DC output. The same 9.2 volt is fed to a regulator that regulates to a 5 volt output. The flash circuit we'll plan on using requires a driver chip, which is a TPS 613205. It just provides an instantaneous burst that we need for the flash to actually function. For the charging battery circuit, we also plan on using another driver chip. It's a BQ25792, and for the battery life, it's between 3 to 5 hours.
And that's our references. And finally, yes, I will like to thank Dr. Wang and also Dr. Almanai for being our advisors and helping us out with this project. And yes, that's it.
Thank you. Hi, Dr. Giacos. Yeah, you can. You have a question, right? Yeah.
Thank you, Dr. Wang. Very good presentation. Excellent job, as Dr. Elmanai says. I have a few questions. Is this a real-time project, a real-time computer vision, correct?
Well, right now, how we set it up, we have it so that it actually just reads an image. However, we are looking at currently constructing a version that'll be able to do a real-time version of this. But right now we just have the image, it just reads an image that we just send it.
Is time acquisition critical to your project? Data acquisition has to be fast or no?
Well, I guess for our project, I guess it's not really a huge, it's not really a issue. Yeah, I don't think that's really an issue because well, it will take time, like depending on like the paper that's used, like the image of the document that's used. I guess that's kind of like varying. Yeah, I guess that's something that varies along like, you know, the page that's used, the background that's used, like variables like that.
Because you mentioned real time. Your project is real time. If it's real time, data acquisition has to be pretty fast. So the suggestion is, in addition to the steps that you're proposing, you can try to do binarizations of the images, black and white, to speed up the process. Number one, okay, to convert the images to binary, black and white. Then I don't know what I didn't follow up what hardware are you using, but especially since you're using edge detection and contours, an FPGA would be very fast to process your information because for two reasons. First of all, you have parallel architecture. FPGA has parallel architecture. For demonstration purposes, it's fine to use an FPGA. If you go to real applications, you can use a system on a SOC or different technology. So your project, you know, Dr. Wang has an expertise from an FPGA computer vision system. So that would be a good project to make data acquisition, make binarization of the images, make edge detection, and look also since you're using dynamic images, the Kani algorithm, how it's going to modify for real-time imaging. The edge detection how it's going to modify for real-time applications is different than static. Okay, so please pay attention to that. So I gave you a few feedback. Binarization of images is going to speed up your project. The inclusion of an FPGA is an embedded system is going to add boost up on your project too because of the parallel and distributed connection. So, and look the algorithms, how they apply edge detection, etc., on real-time applications. That's all I have to. Otherwise, it's a very valuable project. I understand you have to solve a lot of constraints. You have to solve a lot of constraints. My opinion is this. Thank you.
Thank you, sir.
Thank you very much.
Mr.
I think we
Moody,
have another question.
yeah, you're muted.
So that was the video. Yes. We can ask him to type it in. I don't know if that would be feasible. Says never mind.
Okay. Okay, so any other questions? Okay, so thank you, yeah, Dr. Gecko's suggestion, and yeah, so Andrew, please take notes. The first one is that you can convert the image for binary images, so that for past processing, and also consider like the APGA, yeah, APGA for real-time processing, and the third one is the constraints. Yeah, you want to show. Okay. Okay, thank